Welcome back to the deep dive. Today, we're doing something a little dangerous.
Yeah.
We are playing with fire,
Yeah.
but not the way you're thinking.
Yeah.
No matches, no gasoline. We are looking at the fire that happens inside, the brain of a computer,
It is a lot safer than the real thing, but I'd say it's arguably much more complicated.
I'll say.
Hmm.
We are looking at this stack of documentation for a software framework called Optima++.
Mm-hmm.
And I have to be honest, when I first saw that name, I thought it was either a new vision supplement or maybe a platinum credit card tier.
Right.
But no, it's actually a sophisticated tool for combustion chemistry and gas phase kinetics.
It really is, and it's such a fascinating window into how modern science actually works. This isn't just lighting stuff on fire and seeing what happens.
Yeah.
This is about the rigorous mathematical architecture you need to predict how a flame behaves before it even exists.
Right. And this software, Optima++, which comes out of the ELT Reaction Kinetics Laboratory, by the way, it seems to be doing a lot of heavy lifting. But I'm trying to wrap my head around what it is. Is it a simulator? Is it a calculator?
You should think of it more like a rigorous digital laboratory manager.
Okay.
Its mission is to bridge the gap between two very different worlds. The messy, chaotic world of raw experimental data.
Like explosions in a lab.
Exactly. And the clean, theoretical world of chemical models.
So it's the translator between we blew this up and here's the equation for why it blew up.
Precisely. But here's the catch. Optima++ doesn't actually do the really hard math of solving the differential equations itself.
Yeah.
It's a C++ framework, but it acts as a central HUD. It outsources the heavy lifting to external solver packages.
So it's middle management.
Essential middle management, yeah. It connects the user to these industry standard tools like FlameMaster, OpenSmoke, plus Cantera, and ZeroRK. Those are the engines that crunch the numbers. Optima++ is the chassis that holds it all together and, tells the engines what to do.
Okay, let's unpack this then.
Yeah.
Let's talk about building this car. Because looking at the installation notes, this does not look like an App Store download. You don't just click install, do you?
Definitely not, no. This is scientific software, which usually means some assembly required.
Right.
It's primarily built for Linux systems, specifically Ubuntu, though you can get it onto Windows. But the interesting part is that because it relies on those external solvers I mentioned, you have to go out and get them yourself.
I saw that in the notes,
Hmm.
and it seemed surprisingly difficult. Like, for this FlameMaster solver, you can't just download it.
No, you can't. You often have to actually request a password from the developers just to access the installation file.
The password, what is this, a speakeasy? The password is Blue Flame?
It feels a bit like that, but it's really about academic integrity and tracking usage. For OpenSmoke ++A, you might even need to email the developer directly to get the specific version that's compatible.
So it's exclusive. You have to really want this.
You do. It makes sure that the people using these powerful tools are, serious researchers. And once you have these solvers, the engines, you have to manually link them to Optima++ Bren. It's a very modular system.
Okay, so let's assume we've passed the initiation, we got the passwords, we've built the machine, now we need to feed it. And this is where I got a little bogged down. There's a lot of talk about file formats. Why is that such a big deal?
Well, you definitely cannot use a spreadsheet.
Okay.
Remember, we are modeling explosions that happen in microseconds. The data is incredibly complex. So Optima++ uses a format called the Respect Kinetics Data Format, or RKD for short. It's an XML standard.
XML, that's the one with all the tags and brackets, right?
Yes. And the reason they use it is because it is rigid. It's like a straitjacket for your data.
It's a straitjacket.
Yeah, if you have a typo in a spreadsheet, the computer might just ignore it, or you get a weird result. In RKD, the structure is strict. It forces you to be disciplined.
I see.
The workflow involves converting your raw text files into this strict XML. The software even have a check function, literally check XML, that acts like a very angry editor. It verifies your files against a specification version 2.5 right now to make sure you haven't missed a single tag.
It sounds tedious, but I guess if you're designing a rocket engine, you don't want a typo.
Exactly. And think about the variety of experiments. You have ignition delay times, how long it takes for a fuel to light up. You have laminar burning velocities, how fast the flame moves. You have jet-stirred reactors.
I saw that one, jet-stirred reactor. It sounds like a sci-fi blender.
It's essentially a sphere where you mix fuel and air incredibly fast to study the chemistry in a steady state. And the software has to know the difference between that and a shock tube, where you're blasting a pressure wave through gas.
And I noticed the software separates the data into common experimental conditions, and varied values.
That's just good housekeeping. Common is everything that stays the same, like the size of the container. Varied is what you're changing, like the temperature. It just helps the computer organize the chaos.
Okay, so we have the data locked down in this XML straitjacket. Now we need the recipe for the chemical mechanism. But the notes mention a tool called MechModo. And this sounded aggressive.
Hey, MIC-MUD-A is where you stop just observing and start intervening. Before you can test a chemical model, you often need to perform surgery on it.
Surgery is a nice way to put it. I saw commands like remove species or remove reaction. That sounds risky. You're literally deleting parts of the chemistry.
You are. And yes, it is risky. But modern chemical mechanisms can have thousands of species and tens of thousands of reactions. If you try to run that full model, your computer might just crash.
Or take a month.
Or take a month to simulate 1 second of a flame. So you have to trim the fat. You might say, I only care about the main combustion, not soot formation. So you tell MechMod to remove species related to soot. Or you can use Keeplement to say, throw away everything that isn't hydrogen, oxygen, or nitrogen.
It's like editing a book by tearing out pages. You hope the story still makes sense.
That is the perfect analogy. And MechMod also solves the Tower of Babel problem in science.
Which is?
Units. One researcher measures energy in calories, another uses joules. MechMod has commands like switch on it to automatically translate the Arrhenius parameters, the reaction rates, so they all speak the same language.
Okay, so we've built the engine, formatted the data, trimmed the recipe. Now comes the moment of truth. Does it actually work?
Yeah.
This is the simulation phase, right? Mech test?
Correct. Mech test is the simulation engine. It takes that cleaned up recipe and it tries to recreate the experiments you described in your XML files.
But here's my skepticism. Real-world machines are messy. A shock tube isn't a perfect theoretical box. How can code replicate that?
That is the biggest challenge in kinetics, and Optima++ handles it by simulating the imperfections.
Give me an example.
Okay, take rapid compression machines, or RCMs. They use a physical piston to smash gas together and heat it up. But pistons have mass. They don't move instantly.
Right, there's travel time.
Exactly. So Optima++ uses what's called a volume time profile. It literally simulates the changing volume of the chamber millisecond by millisecond as the piston moves. It doesn't just assume it magically compressed instantly.
Wow. So it's not just simulating the chemistry, it's simulating the machine.
It has to. Even for those jet-stirred reactors, it lets you define heat exchange parameters. Because in the real world, no container is perfect. Heat leaks out. If you don't account for that, your model will be wrong.
So you run mech test and it spits out, what, yes or no?
It spits out a file called mech test results. It's a comparison. The experiment said the mixture ignited at 5 milliseconds. The simulation said 7 milliseconds.
A scorecard.
Yes. And if you want to see why it happened, there's a feature called Atom Flow.
I love that name, Atom Flow. Sounds like a visualized meditation app.
It's actually very visual. It calculates the flux of elements. It lets you trace a specific carbon atom from the fuel molecule through all the chaotic intermediate steps until it ends up as CO2.
So you can watch the baton pass in the relay race of atoms.
Exactly. It outputs data for a flux viewer tool so you can see the pathways.
But, and here is the big but. What if the scorecard is bad? Your simulation says something different from the experiment. What do?
You don't panic. You interrogate the model. This is where sensitivity analysis comes in.
An interrogation. Who messed up?
Basically, you have thousands of parameters. One of them is slightly off. Sensitivity asks, if I tweak this one specific reaction rate just a tiny bit, does the answer change a lot or a little?
So you're poking it to see where it's sore.
That's a great way to put it. Optima++ uses a brute force method. It systematically perturbs the parameters, like the activation energy, and reruns the simulation. If a tiny change in one parameter causes a huge change in the ignition time, that is the sensitive spot.
That's the one.
That is the parameter I need to get right.
It seems incredibly granular. The notes say you can even tweak the NASA polynomials.
Yes, those define the thermodynamic properties, how much heat a molecule can hold. You can find out your entire simulation is wrong because the heat capacity of one tiny radical species was off by just 1%.
So we know where the model is broken. We know which knobs to turn. But turning them by hand sounds like a nightmare. There are just too many combinations.
It would be impossible for a human. That is why the crown jewel of this whole software is the optimization module. And it has the best name in the entire industry, FOC2POIS.
F-topopois. Please tell me that means what I think it means. A frantic octopus.
It stands for Focusing Sampling Two-Toe, the best parameter set with uncertainty domain estimation.
That is a stretch for an acronym, but I'll allow it because Foctopus is great. What does the octopus actually do?
It searches for the truth. It uses an algorithm to automatically adjust those sensitive parameters to make the simulation match the experiment, but it does it in a very clever way.
How so?
It starts by casting a wide net generating random sets of parameters. That's the sampling part. But once it finds a spot that looks promising,
Right.
a set of numbers that reduces the error, it focuses. It narrows the search range around that sweet spot.
So it's like a search party. You spread out, and when someone yells, "I found something,"
Yeah.
everyone converges on that location.
Exactly. But there's a really difficult concept here that's central to how it works, the covariance matrix.
Yeah, I saw that term and my eyes glazed over. Map of uncertainty. Help me out here.
Okay, think of it like baking cookies.
I could do cookies.
You have a recipe, you have flour, you have milk. Now, imagine you're not sure exactly how much flour to use. That's uncertainty. But here's the catch. If you add more flour, you have to add more milk to keep the dough right. They are linked.
You can't just change one independently.
Right.
Yeah.
If you treat them as independent, you ruin the cookies. A covariance matrix is just a mathematical grid that tracks those links. It tells the software if you change the rate of reaction A, you probably need to adjust reaction B in this specific way.
So the octopus isn't just turning knobs at random. It knows the recipe.
It knows the relationships. And this leads to the most important rule of Optima plus B. It respects uncertainty bounds.
Which means?
It means you aren't allowed to cheat. You could probably find a set of numbers that makes the graph look perfect, but if those numbers say that carbon has 5 bonds or that a reaction happens faster than light, it's useless.
Right. You fit the data, but you broke the laws of physics.
Exactly. Optima uses these bounds to ensure the result is not just mathematically pretty, but physically real. It finds the best possible truth within the limits of nature.
So let's zoom out. We've gone through installation, XML formatting, the surgery, the simulation, and finally the frantic octopus. Why does this all matter?
Because the era of guess and check is over. Whether we are talking about designing a jet engine that uses 2% less fuel or a rocket that doesn't explode on the launch pad, the margins are just razor thin.
We're at the limit of what we can do by just building things and testing them.
We are. We need to simulate. And to do that, we need models that are nearly perfect. Tools like Optima aren't just calculators. They are truth-seeking machines. They force us to take our fuzzy understanding of fire and harden it into rigorous code.
It's amazing to think about. We've been using fire since the Stone Age. It's our oldest tool. But to take that next step, to really master it, we need C++ frameworks, covariance matrices, and a robotic octopus.
It turns out fire is a lot more than just heat and light. It's data.
A lot of data.
Yeah.
Well, I'm certainly going to look at a candle flame a little differently tonight. I'll be wondering about its laminar burning velocity.
And its sensitivity coefficients.
Don't push it. Thanks for taking us through the invisible math of combustion. And thank you all for listening to The Deep Dive. We'll see you next time.